Hello everyone, welcome back. So let us continue our discussion. We are in 12th week. This is the last week and we are in lecture 2. So this week our topic is buckling, and if you recall the first class we have already defined the Euler buckling load, right? Now just to give you a quick review of what we discussed in the first class, buckling is the behavior of a column, and we also define based on geometry the type of column, and say we have, this is the column and its length is L and flexural rigidity is EI, and if we apply a point load, axial compression, then depending upon the boundary condition, if we consider say hinge, this we have already derived in the previous class. So we get Euler buckling load. We call it P critical, and in fact we derived first the characteristic equation depending upon the different boundary conditions, and for each boundary conditions we defined the first critical load, and if you recall the expression is pi square EI divided by L effective square, and in fact I we can write it as A times R square, and then we can further modify this equation. So we have pi square EA divided by L effective divided by R whole square, and this expression L effective by R is called slenderness ratio, and in fact depending upon the slenderness ratio we can define short column or strut, and then we have long columns, and there is an intermediate column also. So what is the difference? Difference is in their failure mode. So when we have short column, it fails due to crushing, while if we are in long column, it fails due to buckling, and when we are at an intermediate stage, the stress is actually contributed by the axial compression as well as buckling, right? Now obviously in our this course we are mostly worried of long column where it fails due to buckling, and for that we have derived the Euler's formula. Now what are the assumptions behind this Euler's formula? Let us discuss that first, and then we will quickly go through the different other boundary conditions that I asked you to derive the critical load at your end, and then we'll quickly go through the deformed shape. So the assumptions. Now the first assumption is that the column is initially straight and it is axially loaded. The second assumption is the column is uniform. If you look at this diagram here, we have considered the column which is having the same cross section along the entire length, so the column is uniform. Then it is perfectly elastic, homogeneous, isotropic, and obeys Hooke's law. Then obviously L is large compared to lateral dimension. Recall, we defined the slenderness ratio, and this slenderness ratio is based on the length of the column and the lateral dimension. And for buckling, we must have a high slenderness ratio. Next, because we have a high slenderness ratio, direct stress is very small compared to bending stress. And because of this reason only, the governing differential equation, we use the equation of a beam bending, if you recall, EI d2y dx2 is equal to minus n, right? Then self weight of the column is negligible, so it is small, okay, or negligible. And it fails due to buckling. So these are the assumptions we have for this column buckling, right? Okay. Now, before we solve some example or at least check the deformed pattern for different boundary conditions, let us quickly solve the solution, the deformed shape for different other boundary conditions. So let us consider a column of length L and EI is given. So for this column, let us first consider full fixity. So at the ends, this is fixed. So we have y-axis here and x-axis here. And the column is loaded with a force P. And because we have full fixity at both ends, so this end is also fixed, right? So you apply the load here. Okay. Now, under the action of this load, obviously it is going to deform like this. And again, we can consider a section at a distance x from the bottom. Now, because of fixity at the both ends, we will have moment at the ends. So let this moment be m0 and we have the force P acting here. Here also on this end we will have a moment m0. Now for this setup we can write down governing equation, and the governing equation is EI d2y dx2 is equal to minus py plus. So now we can again take this py on the left hand side and rewrite the expression as d2y dx2 plus p by ei times y is equal to m naught divided by ei. Now, for this problem again, on the right hand side we have a non-zero term, and therefore we'll have the total solution as the sum of complementary function and particular integral, and the solution is C1. So let us assume that lambda square is equal to p by ei. So we have solution as cos of lambda x plus C2 sine of lambda x plus the particular integral, which is m0 divided by p. So you can actually put this particular integral here and cross verify the solution. So if you put in place of y m0 by p, you basically get the right hand side. So this is the total solution for the case with fixed boundary condition. Okay, so now again what we have here on the right hand side, C1 and C2, these are the two constants, and that we are going to evaluate from the boundary conditions, right? So the first boundary condition is the displacement y of 0 is equal to 0, and if we put that expression, what we get is C1 cos of lambda times 0 plus C2 sine lambda times 0 plus m0 by p is equal to 0. Now obviously this term goes to 0, and what we have is C1 is equal to minus m0 by p. So we have the first constant C1 evaluated, and it is minus m0 by p. Now we satisfy the second boundary condition. So for the second boundary condition, y prime at 0 is equal to 0, because we have fixed boundary condition. So at this location where y equal to 0, sorry, x equal to 0, y prime, that is the slope, is also 0. So now we have the solution y of x is equal to C1 cos lambda x plus C2 sine lambda x plus m naught divided by p. So if you first find out y prime, we have minus C1 lambda sine lambda x plus C2 lambda cos lambda x, and the third term will be 0. Now if we apply the boundary condition, what we have is 0 is equal to minus C1. C1 is minus m0 by p, so this will be plus and then lambda sine lambda times 0 plus C2 lambda cos lambda times 0. Therefore, what we get is C2 is equal to 0. So you can see we have the deflected pattern y of x is equal to minus m0 by p cos lambda x plus m0 by p because C2 is 0. Now, if we look at the boundary conditions, obviously at x equal to L, we have the deformation is again 0, right? So if we satisfy that condition, y of L is equal to 0, then we get minus m0 by p times cos of lambda L plus m0 by p is equal to 0. Or in other words, we have m0 by p times one minus cos lambda L is equal to 0. Now obviously m0 by p is not equal to 0 and therefore we have 1 minus cos of lambda L is equal to 0. So this is the characteristic equation for the column having fixed boundary conditions, right? Now from this characteristic equation, what we get cos lambda L is equal to 1. So for fixed boundary condition, we have cos lambda L is equal to 1. And therefore, we have lambda L is equal to 0, 2 pi, 4 pi, and so on, right? Obviously, 0 is a trivial solution that we are not looking at. So we have the first critical load is for lambda L is equal to 2 pi. And if we put the expression of lambda, we have square root of P by EI times L is equal to 2 pi. And what we get is P critical is equal to pi square EI divided by L by 2 whole square. So for this case, if you have hinge boundary condition, L effective is equal to L by 2. Recall this is what we identified in the first class and I asked you to derive. So we get the effective length of the column. We will draw the deformed shape and we will see what is the pattern of this effective length for different boundary conditions. But before that, let us quickly solve the other boundary condition, and for that we have a column here Now for this column, we have hinge and fixed boundary condition. So at the bottom we have full fixity. And here we have hinge condition. So let us apply the point load at the top. Say this is P. Obviously the reaction will also be P at the bottom. And the deflected shape is like this. So the slope at the bottom is 0 because we have full fixity here, and because at the bottom we have fixity, so we have a moment generated here which is m0. Now obviously if we need to balance this moment, we must have a horizontal force here, and let this horizontal force be h. Okay. Now again, let us consider a section at a distance x from the bottom. And again, we have the length of the column L and EI is also given. So the governing equation is EI d2y dx2 is equal to minus py plus, if we take the horizontal load at the top, h times L minus x. So that is the lever, right? Okay. Now we can take this py on the left hand side and rewrite the expression. So we have d2y dx2 plus lambda square y is equal to h divided by ei times L minus x, where lambda, as you all know, lambda square is equal to P by EI. Again, in this case, we have y of x, that is the solution of the deformed shape, is C1 cos of lambda x plus C2 sine of lambda x plus we will have the particular integral which is h by p times L minus x. Now again we have these two constants C1 and C2 that we have to evaluate from the boundary condition, and we can easily identify the boundary condition. At x equal to 0, the deformation is 0 and the slope is also 0. So let us first find out the slope and then we will apply the boundary condition. So we have minus C1 lambda sine lambda x plus C2 lambda cos lambda x. And then from the last term we have minus h by p. Okay, so the boundary conditions are x equal to 0, we have y is also 0, and x equal to 0, we have y prime is equal to 0. So let us now put these boundary conditions and see what are the constants. So we have y of 0 is equal to 0. So the equation is C1 cos of lambda times 0 plus C2 sine of lambda times 0 plus H by P into L, which means we have C1 is equal to minus HL by P. Now we can apply the second boundary condition, and for that we have derived this expression. So minus C1 lambda sin lambda x plus C2 lambda cos lambda x minus H by P, that we have to satisfy at x equal to 0. So y prime of 0 is equal to minus C1 lambda sin lambda 0 plus C2 lambda cos lambda 0, and then we have minus H by P. Which means this term is 0, and we have C2 is equal to H divided by P lambda. So what we get is the solution y of x is equal to C1, which is minus HL by P cos lambda x plus H by P lambda sin lambda x plus H by P times L minus x. Now, if we look at the deformed shape here, at x equal to L, again the deformation is 0. So if we satisfy that, what we have here is y at L is equal to 0, which is equal to minus HL by P cos of lambda L plus H by P lambda sin lambda L, and if we put x equal to L, so the third term will be equal to 0, right? Now what we get after simplifying is tan of lambda L is equal to, we have HL by P times P lambda divided by H, which means this is L lambda, or we can write lambda L, right? Therefore, the characteristic equation for this case is tan of lambda L is equal to lambda L. Now, for this, the solution we know is lambda L is equal to 4.5 radian, and there if we put the expression of lambda, that is square root of P by EI times L is equal to 4.5, what we get is P critical is equal to 4.5 square, and that is 20.25 EI divided by L square. Now, this value 20.25 is equal to 2 square. So what we get P critical for this case is twice pi square EI divided by L square. Now we can further modify this. So what we have is L by root 2 whole square. So L effective for this case is L by root 2. Recall this is what we identified in the first class here. So now we get the critical load and the deformed shape for each case. Let us quickly study the deformed shape and what is the meaning of this L effective. So if we consider the first one, so if we have hinge, then we have a deformed shape over the full length. So in this case, L effective is equal to L. The second case we solve is the cantilever beam, and for that we have full fixity at the bottom and the deformed shape is so this is the length of the column, and if you recall, L effective is equal to twice L. That means effective length is between these 2 points, right? So this is twice of L, and that is the L effective. Now if we have the third case, that is we have full fixity at the both ends. So we have fixity here and fixity there, and obviously the deformed shape is like this, and the slope at the two ends are 0. So in this case, L effective is equal to L by 2. So which is between these 2 points. So this is L by 2, and that's the L effective. Now the last one we have solved, and it is having one end fixed and other end hinged. So the deformed shape is something like this, and because we have full fixity at the end, we have slope 0 here. So the effective length, if we mark, is between these 2 points, and this is L by root 2. So L effective in this case is L by root 2. So now you can see deformed pattern under the different boundary conditions and respective effective length under buckling, right? So let us stop here. In our next class, we will solve some problem using Euler's buckling formula. Thank you very much.